So in last lecture we have started with the gravitation from the mechanics tool, and in this lecture we are going to study the satellites. We know that this Earth is revolving around the Sun in a elliptical orbit, which we have seen in a last lecture, which was Kepler's law. Now suppose this is the Earth and this is revolving around the Sun in an elliptical orbit. If there is any smaller body and which is rotating about some heavier body only due to the force of the attraction of the gravitation, then it is called as a natural satellite of that heavier body. Just like moon is a natural satellite of our Earth is much heavier than the moon. Moon is revolving around the Earth and moon is a natural satellite of the Earth. Now there are certain artificial satellites also which are or which can be launched or which are made to revolve around the Earth. Now this is Earth, and there are certain satellites which are made to revolve around the Earth in a circular orbit for the different purposes, like a purpose of the communication, like TV and radio, for some research purpose, or GPS systems for weather forecasting. You can say that these communication satellites or the research purpose satellites and GPS satellites, weather forecasting satellites, these are nothing but just the physical significance of this gravitation. So if you are launching any satellite in particular height, suppose this is a satellite which has launched in a circular orbit, which will start revolving in a circular orbits around the Earth, then this is nothing but the application of this gravitation. We have to calculate how much amount force field is applied on the satellite at a particular height h. So this all things are coming from the gravitational, which are also coming from the Newton's law of the gravitational, which is gmm upon r square. We can say that these artificial satellites which are used for the different purposes are nothing but the physical significances of this gravitational force field. That's why we are studying these artificial satellites. Now artificial satellites, when it is launched in a Earth's orbit, so it is launched by using the two-stage or the multi-stage rocket. So this rocket will consist of generally two stages. I will just draw it roughly. Now this is a satellite, this is a second stage, and say this is a first stage, and this is a satellite which is situated at the top of the rocket. By igniting the first stage, or after the complete burning of the first stage, satellite along with the second stage is reached at a particular height h. By using the second stage, so with the help of the remote controls, it is tilted and it is made horizontal like this. So at the earth surface the satellite was like this, it was in the same position as shown over here, and when the first stage is completely burned and it is made to turn at a 90 degrees and it is made horizontal like this. When the second stage of the rocket is burned, so this rocket will have some horizontal velocity, and let's call that velocity as Vh. There is another velocity which is called as a Vc and Ve. Let Vh is the horizontal velocity, Vc is the critical velocity, and Ve is the escape velocity. When this horizontal velocity is exactly equal to the critical velocity, so the critical velocity is a velocity which is required for a satellite to complete the circular orbits. Therefore, it is called as a critical velocity, or the velocity which is required for the circular orbits. So if this horizontal velocity is exactly equal to this vc, the horizontal, or this satellite will follow the circular path around this earth surface. Now, so this is the first case when this vh is exactly equal to the vc. So at that time, so it will follow the circular orbits. Now suppose if this vh is greater than ve, now ve is the escape velocity. Now if this much amount of velocity is given to any object, so that object is able to escape from the earth's gravitational force field, and this velocity is called as a escape velocity. But obvious, if this velocity is greater than the escape velocity, so the rocket will move in the straight forward direction, because it will not come under the gravitational force field of this earth. Therefore, so the satellite will escape in the universe somewhere. Now suppose if this vh it is less than this vc. Vc is the velocity which is required for the circular orbits. If this vh is less than vc, but obvious, so this rocket will fall down on the earth surface following some projectile path. So it will fall on the earth. And in a fourth case, if this vh is less than this escape velocity, and if it is greater than the critical velocity, it will follow the elliptical orbits. Then at that time, it is possible for the satellite to follow some elliptical orbit around the earth's surface. So this will be the situation. So it may follow the elliptical orbit. So this is the situation then when this ve is greater than this vh but greater than this vc. So at that time the satellite will follow the elliptical orbit. And we know that all these calculations are coming from the Newton's law of gravitation, and thus we can say that the launching of the satellite is completely the physical significance of this gravitational and the Newton's law of gravitation. Suppose m is the mass of the satellite, capital M is the mass of the earth, and r is the radius of the earth. Then the gravitational force field applied on the satellite at height h, that is given by, so this, let me call this as a F, gravitational force field, which is equal to gmm upon r plus h bracket square. So this is distance between the, so this is r, which is the radius of the earth, and this is height. So we know that according to the Newton's law of the gravitational, the force is, gravitational force field is directly proportional to the masses between them and square inversely proportional to the square of the distance between them. So the distance is r plus h, which is at the denominator, and masses are, capital M is the mass of the earth and small m is the mass of the satellite. So the gravitational force field applied by the earth on the satellite at a particular height h, so that is given by F is equal to gmm upon r plus h bracket square. If we consider the situation where this vh is equal to vc and the satellite is following the circular orbits, then the centripetal force required for the circular orbits, that is given by mv square upon r plus h. Now this v is equal to nothing but the vc, or the horizontal velocity of the object, and for the circular orbits to follow, these two forces must be equal. So we can write this gmm upon r plus h bracket square is equal to mv square upon r plus h. From here I can derive the equation for this v. So this m will get cancelled, So this square and r plus h will get cancelled, and what I am left with is v square is equal to gm upon r plus h, or I can write, so this v is equal to square root of gm upon r plus h. So from this equation we can see that this horizontal velocity is independent of mass of the satellite. It means that whether the satellite is of a 2 kg or if it is a 10 kg, or even if any object wants to rotate about the earth in a circular orbit, then the whatever horizontal velocity is required for that, it will be same for all the objects for a particular height. Yes, of course, if this h changes, this v will change. Okay, but it is independent of mass of the object. See, if this g dash is the acceleration due to the gravity on the satellite at height h, it is given by gm upon r plus h bracket square. Or if I multiply by r by h on a both side, r by h, it will give me gm upon r plus h. Now if I put this value of gm upon r plus h here in this equation, I am going to get v is equal to square root of this g dash into r plus h. So this is the relation between the horizontal velocity and acceleration due to the gravity at a particular height h. So moral of the story of this lecture is that you can have artificial satellite revolving around the earth at a particular height h, and you can do all the complicated calculations starting from the gravitational force field and the Newton's law of the gravitation, which is given by F is equal to gmm upon r square. So the artificial satellites are launched in a different orbits of the earth for the communication, for the research purpose, for the GPS purpose, and for a weather forecasting. Now when these satellites are launched at a particular height, the job is done with the help of a two-stage or a multi-stage rocket. First few stages are used to launch the satellite at a particular height. Afterwards they are made to tilt by 90 degrees, and the second stage it is used to ignite the satellite and give it a horizontal velocity. When the horizontal velocity is given, the four cases arises when this horizontal velocity is exactly equal to the critical velocity. The critical velocity is the velocity which is required for the circular orbits. Then the satellite will follow the circular orbits when this VH is equal to VC. If this VH is greater than this VE, VE is the escape velocity which is required to escape any object from the Earth's gravitational force field. If this VH is less than VC, VC is the critical velocity. So if this VH is less than VC, the satellite will fall on the earth following some trajectory path. And if the horizontal velocity it is less than V, but if it is greater than VC, so the satellite will follow the elliptical orbits. The critical velocity which is required for the satellite to revolve in a circular or in an elliptical orbit, it is independent of mass of that object.